So this is Math 140, Calc 2. This is lecture 9, if my counting is correct. And today we're going to be talking about areas between curves, volumes, and trig substitution. It is a beautiful snowstorm outside. It's not great snowpacking material right now, but as it warms up, it might be. If anybody is interested in going to Spoon later today to get some gelato or frozen yogurt to celebrate the winter, I would much rather do lickety-split, but if you take what's open, just shoot me an email. Hi, so what are we doing today? So again, key ideas are area between curves, volumes, and trig substitution. This comes down to two very different topics. The first is an application. So why do we care about integration? What does integration give us? Well, one of the things it gives us is it lets us find areas between curves. Another is we can actually use it to find volumes, and you can keep going up the ladder. To do this, we're going to use the fundamental theme of calculus in practice and say that areas under the curve is related to the antiderivative at b minus the antiderivative at a. Well, in order for the fundamental theme of calculus to be useful, what do you need to be able to compute? If we're going to use the fundamental theme of calculus, what do you have to be able to find? Integrals, right? It does us no good to say the area under the curve is the antiderivative at b minus the antiderivative at a. Well, what's the antiderivative? Oh, I don't know. So we need more techniques to find antiderivatives. So we talked about integration by parts, which is an extremely powerful technique. And we said that sometimes it's not so easy to figure out how to use. For one of the examples, when we had the natural log of x, the best way to view it was the natural log of x times the function 1. And when we viewed it that way, all of a sudden we could use integration by parts. It requires two inputs. So we're going to use the fundamental theme of calculus. We have to be able to find antiderivatives. And so the goal of today is to give an application and also to talk about another method of finding antiderivatives called trig substitution. It's not surprisingly very similar to U substitution. It's using trigonometric substitutions. All right, so let's do area between curves. The simplest case is if we start off something like this, and maybe what we'll do is we'll take one curve to be the x-axis, and then maybe here's the other curve. Okay, and so if I take maybe my points, here's my point A, and here's my point B, then the area under the curve, or between the curve and the x-axis, would be the region in red. So this is the area between y equals f of x and the x-axis. So when we do it like this, we note that some of the area is counted as positive because it's below the curve and above the x-axis, and some of it counts negative. So this part over here would be, we count positive area, and over here, this would count as negative area. And so we're just finding the total signed area between the two. And so we would do this as the integral from a to b of f of x dx. And this is the signed area. The actual area would be the integral of what? So if we didn't care to have the stuff below counted negative and the stuff above counted positive, what would I integrate? Instead of integrating f of x, what would I integrate? Well, if I integrate f of x, the stuff over here can count positively, and the stuff down here is going to count negatively. Here, f of x is positive and it counts as positive area. Here, f of x is negative and it counts as negative area. So we have a question, not f of y. So we could do it separately. But right now, if we just integrate f of x, where f is negative, it counts as negative. Where f is positive, it counts as positive. What if I just want the true area between them? Its absolute value. And so what I can do is I could integrate the absolute value of f of x. And so if I integrate the absolute value of f of x, that's going to give me the area between the two curves. Normally, when we talk about area between curves, we don't care if it's positive or negative. We just allow the positives and negatives to cancel. If I just care about the actual physical answer, like I'm taking a piece of paper and I'm cutting it, and I just want to see what it is, then you don't want to have the positives and the negatives cancel. If you had to do this, you would probably split the integration to the point where it's positive and the point where it's negative, because the absolute value of f may have a slightly different derivative and a slightly different antiderivative. So if I want to move on and give an example, let's say I have curve 1, y of x is equal to x, and y2 of x is equal to x squared. Where do these functions intersect? So one is at 0, 0. Where else do they intersect? And so from zoom land, they also intersect at 1, 1. And one way to see this is we could set y1 of x equal y2 of x. So x equals x squared. Therefore, x squared minus x equals 0. X times x minus 1 equals 0. So x is either 0. And so if we plot them, it will look like this. The line is going to be above the parabola when we go from 0 to 1. If you, I'm sure, take a point like 1/2. If you square 1/2, you get 1/4, which is less than 1/2. So in the interval from 0 to 1, x is larger than x squared. From 1 onward, x squared is larger. So if I want to find the area under the curve, I would have the following. So the area is going to be the integral from 0 to 1. Which curve is above, y1 or y2? So it'd be y1 of x minus y2 of x dx, or the integral from 0 to 1 of x minus x squared dx. Okay, so for this problem, would I want to factor x minus x squared? Would I want to write this as x times 1 minus x and then try to integrate it? Or do I want to keep it as x minus x squared? Yeah, x minus x squared, because I can then integrate this term by term. If I write it as x times 1 minus x, oh, this is a product. So this is going to be the same as the integral from 0 to 1 of x dx minus the integral from 0 to 1 of x squared dx. So the first one is just x squared over 2 at 0, 1 minus x cubed over 3, 0, 1. So it's 1/2 minus 1/3 is 1/6. So the area between the two curves is just going to be 1/6. And so this is how you find the area between two curves. You need to be able to have a good explicit formula for the top, a good explicit for the bottom. Depending on what you have, it might switch which one is top and which one is bottom, in which case you would have to break it up. So for example, if I give you, say, something sinusoidal, and I want to find the area between that and, say, a curve like this, it could change which one's on top, which one's on the bottom. If I just care about sine quantity, it's not going to matter. If I care about the actual physical area, You might have done some optimization problems in calculus a long time ago when you have Farmer Brown and he loves rectangular pen for his cows. And now that you're at Williams, knowing how to box in cows is a useful skill. And you try to figure out what's the best shape that you could have. Sometimes when you do problems like this, you get a negative length. And you just know that I can ignore a negative length. That's not going to come into play. So you have to just be careful as to what are we trying to study. All right, let's do an interesting problem now. What is one of the most important three-dimensional shapes you can think of? A cube. Okay, so let's start off with a cube. So I can view a cube as I have a square down below, and I come up something like this. And so I could view it as, at each point down below, in the bottom, I have a height. And so if I want to view it like that, this would become a two-dimensional integral. And this is where multivariable calculus, the sequel, comes from. And so now, rather than just integrating over a line, I would integrate over a plane. And it's actually very easy to integrate over regions like rectangles and squares. What's another shape we might try to do in 3 dimensions? Pyramid. But there's a really nice shape that we have ignored. Sphere, right? We like spheres as well. This is, the generalization of the circle. And there are 2 ways to view the sphere. One way to view the sphere is I have a circle and I give you a height above each point. And then that would be a 2-dimensional integral. So if we knew multivariable calculus, that would be a great way to do this. However, we don't know 2-dimensional calculus. So the question is, can we do these problems in 1 dimension? And what we could do in 1 dimension is maybe this is a cube of height 1. So I have my x-axis going from 0 to 1. And at each point over here, I'm attaching a small infinitesimal box. And it's always going to have the same side length. Yes, there's going to be dx. So box of size 1 by 1, thickness dx. And so the volume would be the integral x goes from 0 to 1 of 1 squared dx. More generally, if it was L by W by H, it could be the integral x goes from 0 to H, L times W dx. And that would get me the volume of a cube. I should really do this as a 2 or 3-dimensional integral. But given that this is Calc 1, we're not supposed to be doing integrals in several variables. Well, I could at least give you a little bit of a sense of what's coming down the line. If you continue with calculus, what will you see next? But frequently, there are ways to do some tricks and reduce what we're studying. And so if I view it as just my height is along the x-axis, I can now reduce this to a 1-dimensional integral. For the sphere, I can do a similar trick. And so if you look at the cross sections of a sphere, I unfortunately had built a nice sphere with some of my kids yesterday, but I left it at home. So let me just put this on so people in Zoom can see. So we will use this as always to approximate our sphere. Okay, so I've got it oriented so my x-axis is coming in this direction. As I slice it, what does it look like every time I take a slice? It looks like a bunch of circles. So we can try to figure out what is the volume of a sphere by looking at a bunch of circular slices. So do circular slices. So do you want to integrate over the entire sphere or just half a sphere? Yeah, let's have x go from 0 to 1 and then just double. So the sphere is x squared plus y squared plus z squared equals r squared. Do you want to do a general R, or do you want to do the special case when R equals 1? I will do R equals 1. So what we're going to do is here's 0, here's 1. Here's a value of x. And then I have a circle over here with some infinitesimal thickness. And I'm going to have a bunch of circular rings. So a bunch of circular rings. So if I give you a value of x, we have to figure out what is that radius. So here is my x. I have a radius of 1. So what do you think this number is over here? And for my sphere. How far can I go? What's the radius of this little disk? So what will be the thickness of the disk? What's the R? So we have x squared plus y squared plus z squared equals 1. So we'll do the special case when I equals 1 here. So what do you think the radius will be of this little disk? Do you think the radius depends on x? So do you think the disk has a different height depending on what x is? So when do you think the disk has the smallest height? Okay, so you think it's going to have the smallest height at both 0 and 1. So one of them is going to be the smallest height. So when x equals 1, how far up can you go for the radius? You're at the extreme edge of the sphere. Right? Let's look at it again. So this time you put zoom in. So we've got our thing oriented like this. When x is equal to 1, if this is the perfect sphere, it's just a point here. What's the radius going to be? How high up can we go? How far can we go from the x-axis at the very end? 0. And when I take x equals 0, that's at the maximum possibility. How high up can we go now? 1. So without solving the whole problem, we at least have some intuition of what's going on. So now let me just go back and share the screen again. So when x equals 1, r equals 0. When x equals 0, r equals 1. And in general, it's going to be x squared plus r squared equals 1. So r squared is 1 minus x squared. So r is the square root of 1 minus x squared. That's going to tell us how far we can go. And so what is the volume of a disk of thickness dx and radius r? It has volume. So what is the volume of a disk of radius r and thickness dx? Excellent. It's pi r squared, the area of the base, times dx. So the volume is going to be twice the integral. X goes from 0 to 1 of pi r squared. I'll write it r of x squared. This is r of x dx. which is 2 integral x goes from 0 to 1 pi. Oh, life is good. We see that the radius is the square root of 1 minus x squared, and we worry this is not going to be a pleasant integral to do. But we get to square it. And so what's the square of the square root of 1 minus x squared? One minus x squared. And so now we have the integral that we need to do to find the volume. And if we can figure out this integral, we will know the volume of the sphere. So what we're doing is we are finding the volume of a sphere given the volume of a circle. Okay, any questions on what we've done up till now? So we need to compute twice the integral from 0 to 1 of pi 1 minus x squared dx. If radius capital R, it would be twice the integral from 0 to r of pi r squared minus x squared dx. So it's just good to know how things would change if we looked at the more general case. Okay. How should we do the integral of pi 1 minus x squared? How should we handle that integration? So how would you integrate pi 1 minus x squared? What's the first thing you might do? So if you're using integration by parts, you have to choose what's u and what's dv, right? So what would you choose to be u? What would you choose to be dv? So you could do this by integration by parts, but it's going to be more work than you need to do. It's not wrong, but it's more work. What's the first thing you should think of when you have this integral? Good. So step one is move pi outside. So it's 2 pi integral from 0 to 1, 1 minus x squared dx. Let's move the constant out. So that's step one, the constant. How should we handle 1 minus x squared? We could do integration by parts, but there's something else. I'm sorry. Yeah, just use the subtraction rule. The integral of a difference is the difference of the integrals. So this is going to just be equal to 2 pi, the integral from 0 to 1 of 1 dx, minus 2 pi integral from 0 to 1 of x squared dx. Or more generally, it would be 2 pi integral from 0 to r of r squared dx minus 2 pi integral from 0 to r of x squared dx. You want to do the more general case. And now we just need to find what function has derivative 1. X. So this would just become 2 pi x at 0, 1 minus 2 pi. Now what function has derivative x squared? 1/3 x cubed. So x cubed over 3 at 0 and 1. And if we did it the other way, it would just be 2 pi r squared x at 0 and r minus 2 pi x cubed over 3 at 0 and r. All right, so for the first one, we just get 2 pi minus 2 pi over 3, or 2 pi r cubed minus 2 pi r cubed over 3. So this is going to just be 2 pi minus 2/3 pi. I multiply the first one by 3 over 3, so it's 6 pi minus 2 pi is 4 pi over 3. So this is going to just be 4/3 pi, or 4/3 pi r cubed, the volume of the sphere. And so, assuming we know how to find the area of a circle, we've just figured out how to get the volume of the sphere. at least, if you remember your formulas, you should remember, oh yes, it's the 4/3 pi. I want to just quickly give you a mnemonic for remembering things. And so what we're going to do is we have here, we're going to have a circle, and here we're going to have a sphere. And here we're going to have the area, the perimeter, and here we will have the volume, we'll have the surface area. And can anybody give me the area of a circle of radius r? Pi r squared. And what is the perimeter of a circle of radius r? 2 pi r. Do you notice anything? It is the derivative, right? This is a derivative. What is the volume of a sphere of radius r? Yeah, we just did that a moment ago, right? 4/3 pi r cubed, it's the right. Does anybody remember the surface area of a sphere of radius r? Four pi r squared. So I have to ask, did you really remember that? Okay. So I asked, did anybody remember it? And you misled me. So how did you get this right? So this is even better than remembering, right? You looked at the data and you made a conjecture. I get the perimeter by differentiating the area. The perimeter is one dimension lower. Maybe for spheres, the surface area is going to be the derivative of the volume. And the answer is yes, that is correct. So the question is, why is this true? And so let's just do a circle. So in the interest of time, I'm only going to do the circle. So here is a circle of radius r. And then, not to scale, I'm going to increase the radius by a small amount, delta r. So the big circle has area pi r plus delta r squared. The smaller circle area is pi r squared. So the difference is the ring. And that has area pi r squared plus 2r delta r plus delta r squared minus pi r squared, which is just 2 pi r delta r plus pi delta r squared. If I wanted to approximate this, it doesn't seem like it's a terrible thing to just say it's the perimeter times the thickness. Does that seem reasonable? You've got to be careful with arguments like this, but maybe, perimeter times the thickness should maybe be approximately the area of the ring. We've got to be a little bit careful because things curve. But so then that would mean the perimeter times delta r should be approximately equal to 2 pi r delta r plus pi delta r squared. So the perimeter should be approximately 2 pi r plus pi delta r. And what happens to pi delta r as r goes to 0? As delta r goes to 0, what does this go to? Yeah, so goes to 0 as delta r goes to 0. And so here's a rough sketch of why the perimeter should be essentially the derivative of the area. And as a nice exercise, you can extend this to the sphere and the surface area of the sphere. But what's nice is, if you remember just some of these relations, once you remember this, you can actually get the rest. So if I remember that I take the derivative or the antiderivative, if I know one, I can get the other. Does anybody know what happens on March 14th at around 1:59 p.m.? And it is Pi Day, right? 314 March 14th. Because in America, we have the stupid notation of doing the month first and then the day. 159, people 14159. So there's a huge debate among a very small set of people as to what is the right constant. Is it pi? Is it 2 pi? Is it 4 pi? Is it 4/3 pi? It depends what you think is the fundamental object. Is the fundamental object the area of the circle, in which case we're going to make the constant pi, or is the fundamental object the perimeter, which we would make it 2 pi? Or if you do physics, sometimes you talk about flux in physics, and it's the surface area, it's 4 pi. So if you've done electricity and magnetism, you might have seen the constant, 1/4 pi epsilon naught in electricity and magnetism. So all of these constants can have cases made for them as to which is the one that is the most relevant. All right, so what I want to end with now is talking a little bit about trig substitution. And so the whole purpose of this is we have a lot of integrals that are hard to do. The goal is to convert an integral that's hard to do to one that we already know how to do. And so depending on the type of substitutions we do, we can often make things much simpler. So we've talked a little bit about, I think, U substitution. And the idea is if I give you f of g of x, its derivative is f prime of g of x times g prime of x. So if I integrate the derivative of f of g of x, that's the same as integrating f prime at g of x times g prime of x. So what function has derivative, the derivative of f of x, of f of g of x? So what function has derivative, the derivative of f of g of x? F of g of x. So when I ask for the antiderivative of the function whose derivative, well, that's just f of g of x. And so f of g of x is just the integral of f prime of g of x, g prime of x dx. So for this to be useful, we have to recognize when we have an integral that's of the form f prime evaluated at g times g prime of x. So frequently, we will let u equal g of x, du dx is g prime of x, or du is going to be g prime of x dx, and then we get f of g of x is just the integral of f of u du. Sorry, f prime of u, sorry, f prime of du. And then this just becomes f prime evaluated at u, which is just, I'm sorry, this becomes f evaluated at u, but that's really f of g of x as u equals g of x. So this is U substitution. When I can recognize that I have something of the form f prime at g of x times g of x, then I'm in great shape. So sometimes it's not hard to recognize that we have something like that. And again, the more problems you do, the easier it's going to be to see stuff like this. And so, for example, let's say I give you the integral of x squared e to the x cubed dx. So when you see an e to the x squared, that's a tough function to integrate. But I have an x squared in front of it, and that's probably not by coincidence. If I were to take the derivative of e to the x cubed, what would you get when you take the derivative? squared times the derivative of x cubed. This is the chain rule, and it's e to the x cubed times 3x squared. So notice that this almost looks like the derivative of e to the x cubed. It's just off by a factor of 3. And so this suggests that we should be able to evaluate this integral without too much trouble. And doing this by u substitution, we could let u be what? Let's let u be x cubed. So du dx is going to be 3x squared, or du is 3x squared dx, or we have an x squared dx, so x squared dx is 1/3 du. So our integral, x squared e to the x cubed dx, would just be the integral of e to the u times 1/3 du. When I'm integrating e to the u 1/3, what's the first thing I do? It's the very first thing I should do. Pull out the 1/3. So now I have 1/3 integral of e to the u du. Okay, now what do I do? So what do I do now? Yeah, so what function has derivative e to the u? It's just e to the u. So I would just get that this is just 1/3 e to the u, but that's just 1/3 e to the x cubed as u is x cubed. So this is how we do u substitution. The goal is to try to say, I have something of the form f prime at g of x times g prime of x. And I've got to recognize that I have something of that form, and then I let u be g prime. And I let u be g of x. Okay, trig substitution is somewhat similar. So my son is in pre-calculus right now, and they were told that you don't really need to remember a lot of your trig identities. To some extent, this is true because this is the 21st century. You have access to online searches. You can look things up very quickly. But the more things you remember, the easier it's going to be to see relationships. There is, I think only 3 homework problems in one of the near future assignments, but some of them take a while. The first one is hard. There are 3 different ways to do it. If you remember your trig identities, there's a really fast way to do it. If you don't remember your trig identities, it can take a little bit longer. And so the more you remember, the easier it's going to be for you to see relationships. And so let's say I want to integrate from 0 to 1, 1 over 1 plus x squared dx, or maybe the integral from 0 to infinity of 1 over 1 plus x squared dx. Both of these are extremely important integrals. The second one is a little bit harder because we have to first make sure that the integral is actually finite. 1 over 1 plus x squared, whenever you see a fraction, what's the first fear that you always have? Is the denominator 0? Fortunately, 1 plus x squared is never 0, so we don't have to worry about dividing by 0. But if I integrate off to infinity, I have to worry about, is this going to be finite or is it going to be infinite? It turns out it is decaying fast enough that it is finite, so we're okay. Both of these integrals are extremely important. The second one is very important in probability. The first one is important in theoretical mathematics. It actually leads to a beautiful formula for pi. So trig substitution starts with the following. So trig substitution starts with the following. What's the most important relationship you can remember from trigonometry? Excellent. I've always learned it as sine squared x plus cosine squared x equals 1, but it's essentially the same. There are 2 other identities you can immediately get from this by doing something to both sides. And they involve the other trig functions. What could we do to both sides? So what are other trig functions we like? We have sines, cosines. What else do we have as a good trig function? What are the other basic trig functions? Tangent. How can we get a tangent? Tangent is, what's the definition of tangent? Good. So tangent of x is the sine of x over cosine of x. If we divide everything by cosine squared, we get tangent squared x plus 1 is 1 over cosine squared, which is secant squared. And if we divide everything by sine squared, we get 1 plus cotangent squared x is cosecant squared of x. So these are three very useful identities. It's really the Pythagorean formula and then just dividing by sine squared or cosine squared to get this. So the idea is, if I see a 1 plus, hey, wait a minute, maybe I make a change of variables. And actually, rather than using x, I'm actually going to just change all the x's to theta. Because I've already written the integral above with an x. So let's just change these all to theta. So if you see 1 plus x squared, think x equals tangent theta. If you see 1 minus x squared, think x equals secant theta. Because if I have tangent squared plus 1 equals secant squared, oh, no, I'm sorry. No, not secant. I would want to do cosine. Sorry. Think x equals sine of theta or x equals cosine of theta. You're solving from, sine squared theta is 1 minus cosine squared theta, or cosine squared theta is 1 minus sine squared theta. So these are really good substitutions to think about. So when I have my integral 1 over 1 plus x squared, I look 1 plus x squared. Okay, maybe I should take x to be tangent theta. And so we have the integral from 0 to 1 of 1 over 1 plus x squared.
Wait, I just have a question.
X to be tangent of theta. So when x goes from 0 to 1, I have to figure out first what is the range of theta. So when x is 0, what angle has a tangent of 0? Draw things. When x equals, what angle has a tangent of 0? So again, if this is my angle theta, this is x, this is y. Tangent of theta is y over x. So what angle has a tangent of 0? 0. And what angle has a tangent of 1? So that would be where y equals x. (45 degrees), but we always use radians. So pi over 4. So pi over 2 is 90 degrees, pi over 4 is 45 degrees. We always use radians because the derivative of sine is cosine, derivative of cosine is negative sine, only if you use radians. Okay, so we now have the beginning of our conversion factors. We know x goes from 0 to 1 becomes theta goes from 0 to pi fourths. When x is equal to tangent theta, we need to figure out what is dx d theta. Does anybody remember what the derivative of tangent is? Here's a question. So the question is, why would we think of x equals tangent theta when we see 1 plus x squared? And so the reason is, if you look over here, if I take tangent of theta to be x squared, I see x squared plus 1 equals secant squared. This is a way to replace a 1 plus x squared with something nice. Similarly, I could rewrite the top one as 1 minus cosine squared of theta equals sine squared theta, or 1 minus sine squared theta is cosine squared theta. So if I see something of the form 1 minus x squared, if I take x to be either sine or cosine, it's going to give me a nice switch. So does anybody remember what the derivative of tangent theta is? It's secant, almost. It's close to secant. It's close to secant. Secant squared of theta. And you can get this by doing the derivative of sine of theta over cosine of theta, and then what rule do you use? And then you use the quotient rule. So now this integral becomes the integral theta goes from 0 to pi over 4. And again, you can see I love putting in extra notation all over the place to keep track of what's my variable, where variables go from. We have 1 over 1 plus x is tangent, so it's tangent squared of theta. Dx, well, dx d theta is secant theta, then that means dx is secant squared theta d theta. So we get secant squared of theta d theta. But what does 1 plus tangent squared of theta equal? Secant squared of theta. It's almost like I like you guys, right? And have deliberately chosen something that's going to work out nicely because I'm the one at the board. So I have secant squared theta, and I divide by secant squared of theta. So what's secant squared theta divided by secant squared of theta? 1. So this is just the integral. Theta goes from 0 to pi over 4 of 1 d theta. All right, well, what function has derivative 1? Well, we're not using x as our variable. So what variable would we use? Yeah, it would just be theta. And so this would just be theta evaluated 0 and pi over 4. So it's just pi over 4. So this integral is actually 1/4 pi. And we will see later we have pi over 4 equals the integral from 0 to 1 of 1 over 1 plus x squared dx. We will see later that this is 1 minus a third plus a fifth minus a seventh plus a ninth minus an 11th. That there's a really beautiful proof of this. And so if you look at the alternating sum of the reciprocals of the odd numbers, you actually get pi over 4. So let's end with one more problem for you to think about. So let's say I give you a quarter circle. And so if this is x, this is the square root of 1 minus x squared, because it's a circle of radius 5. And so the area of the circle is going to be 4 times the integral x goes from 0 to 1. And the height is just the square root of 1 minus x squared dx. And so if we do trig substitution, we have a 1 minus x squared. What should we try for x? There's two possibilities. Sine or cosine. Given that x goes from 0 to 1, I'm going to choose sine. So if I choose x to be the sine of theta, as x goes from 0 to 1, theta goes from what has the sign of 0? 0. And what has the sign of 1? So it matches up nicely. So dx d theta, derivative of sine is just going to be cosine of theta. So dx is equal to cosine theta d theta. So the area is just 4 times the integral theta goes from 0 to pi halves, the square root of 1 minus sine squared of theta times cosine theta d theta. And what is the square root of 1 minus sine squared? Square root of 1 minus sine squared is square root of cosine squared. So I'm going to just get cosine squared of theta to theta. So we'll stop here, but there are ways to evaluate this integral. All right, so this is trig substitution here. The more problems you do, the easier it gets to be. All right, enjoy the weather outdoors.